algebras or phenomena algebras. So it would be great if we had a good notion of a spectrum for these things, so that we could have algebra on the one hand and the space on the other side of things. We would like to go back and forth between the two. And one other things this could provide us with a deeper geometrical and topological insight into quantity. And this has been tried a lot of times, as you can imagine. It's an important notion, and there are pretty different ideas. You can try different things to get to non-commutative space. And I want to just mention just two things we may want to do. Many people have said we have to incorporate the non-commutativity by introducing a non-commutative topology. This was first done in functional analysis, late 60s, early 70s, by Neumann, Charles, Kummer. And then later this became a theory of quantiles. Malby, Wozinski, and lots of other people. In physical terms, this corresponds to an operational view where you ask questions. You ask your systems some questions, and we know from theory it may matter in which order you ask these questions. So the questions roughly correspond to the open sets in the non-commutative topology, and this is why your meat becomes non-commutative, because this order in which you ask the questions matters. Another idea that you may have is that you could incorporate non-commutativity in the form of a lack of points. I'm not actually aware if this has been done by other people. This is roughly what I would suggest today. What's the idea here? The idea is that if you have a non-commutative spectrum, this is could be a space without points, let's say a local or frame without points, and the physical intuition is that points act as models or states of a theory whose propositions are represented by the open sets in such a space. And if you had points, you have these models, you could assign values to all these quantities, and we know by Cauchy spectrum that you can't do so. So maybe the non-commutative space should have no points. So now I want to introduce one object, which of course will be the object that I suggest as kind of non-commutative spectrum. So let's start from the system algebra, which has a unit element, and we look at its abelian subalgebras. The abelian subalgebras all have a unit element too, and all these unit elements are just the same as the unit element in the big algebra, so it's a condition there. And they form a partially ordered set just under inclusion. This is this V of A here. Now I define a certain functor on this, and that's called the spectral presheaf, and it's defined very simply. To each abelian subalgebra, you assign its Gelfand spectrum. So this is, if you like, the space of characters of the algebra, it's equipped with economic topology. That's the same thing you have in the commutative case, because locally at each of the it is. Now we have to do something about these inclusions. So we need certain functions between these spectra, and it's also very simple. Let's say you have an inclusion of a small algebra C prime, which is bigger than C, the right inclusion is I C prime C. Then I get a function from the spectrum of the bigger one into the spectrum of the smaller one. It's this function here, C prime I C prime C. It's very simple. You just take an element of the bigger space, such a lambda, which is the character of the algebra, and restrict it to the smaller algebra. And this function is well known to be continuous and surjective. And that's the main object, so I want to argue that this object, the spectrum presheaf sigma A, has some properties of the spectrum of this non-commutative algebra A. And I'll make some very basic and complete observations. There should be more to be said. But where does this come from? Well, it comes from this Topos approach to quantum theory, and there this object plays a role as an analog of the state space for a quantum system. And you can show quite easily that as a presheaf it has no global elements. And this is exactly the notion that would means that this, in this particular sense, is a space without points. And you might think it's just too simple to look at these commutative parts and there can't be much interesting content here. But actually, you can do quite a lot with this object. So you can show, for example, if you start from a phenomenon algebra, which has no type 1, 2 sum, this is roughly excluding 2 by 2 matrices. Then there exists a projection between the state space on your phenomenon algebras, all the quantum states GC is a continuous function, it's just this ordinary Gelfand map, and if you do this for all your C's, it's very straightforward to see that these G's are just the components of a natural transformation between these two presheafs, so you actually get an arrow, and the top was set the A op, and you get a subobject of sigma A as the image of sigma B. And this subobject is written by first y star, then G applied to sigma B. And this now actually is something which actually lies within sigma A. And this just means we have shown that every star homomorphism between arbitrary C-star algebras gives us a map between the associated presheafs, associated noncommutative spaces in the opposite direction. And you can see this, if you like, as the first half of a noncommutative Gelfand transformation. This is exactly what we did. We went from algebras to spaces. And morphisms between the algebras were mapped to morphisms between these spaces. Both these components of the map are directly induced by this morphism between the algebras. So phi star is this inverse image part of geometrical morphism, directly induced by this map that the phi G is the Gelfand transformation, also directly coming from phi. You can do a very nice thing for non-integrals. Now, is it useful in some sense? Well, first of all, this may be useful in itself, because it may establish that this is actually the notion of a non-commutative space, but you can look at things that follow from this, and one is just looking at groups. So, unitary groups are often important in quantum theory, and what's it going to mean here? If you have a unitary operator U, that, well, that's actually nonsense what I'm saying here. It's not supposed to commute, it's just acting on U. It's not supposed to commute with all elements of X, but it's supposed to map A to itself. Sorry about that, that's nonsense. So I actually mean unitary groups acting on the algebra A and mapping into itself. Such unitaries play a central role in quantum theory and serve to encode time evolution of the system, symmetries, and also covariance properties. So we'd like to have them in the game, and if, as we suggest, our spectral presheaf sigma A is like a state space for the quantum system, then this group of unitaries should act in this space by automorphisms. And that's a little application of what we did. Namely, if you take a unitary operator U, it induces a star homomorphism of your algebra. You just send an operator A to U A, actually U to the minus 1 A to U. Let's do it this way around. Just as before, this induces an automorphism of the underlying process of the subalgebras, and as a geometric, in this case, automorphism of the topos. This is just one topos in the game because we just map the algebra A to itself. It still works the same way as before, and you do these two steps, phi star and then G. And in this case, you map sigma A into itself. So what's happening here? It becomes much clearer if we look at how this is acting on the subobjects. So let's take all these open subobjects. Just look at the definition. So what happens at the abelian C at this component, GC acting on this, well, this GC acting on S, L of UC. So L of U is just U to the minus 1 C U. So it's a commutative subalgebra, which is isomorphic to C, but rotated by U, if you like. And then by GC, just shift this back into sigma AC to this component. So it just means the old component, which was at U to the minus 1 CU, is now rotated into position C. So your subobjects are actually rotated by the unitaries as you expect. It's easy to see that if you look at transformation for U to the minus 1, you would rotate back and compose these transformations. So you actually get a faithful center of A. The topos then becomes, well, this thing obviously I write this change constant as BZ as center. So if A is commutative, then it's equal to its own center, of course. The poset just contains one element, namely A itself. The topos becomes set to be A op, but this is a single element, so it's just set. The spectral presheaf then simply is the Gelfand spectrum and a little set as you would like to. Just as a remark, if you do the same thing for noncommutative algebras, you of course still get a non-trivial poset. And the construction I showed of this G after phi star, this arrow between non-commutative spaces, this construction works just the same because it was stage-wise. So it's really my choice which poset it would be. Let's not go for something. There are many open questions, clearly. So this map that I showed you is composed from the composition of the unit image part of geometrical morphism and net transformation. It can be seen as a map between particular presheaf topoi with distinguished state objects, sigma, and clearly need an explicitization of those. So I would like to be able to say something as neat as category of complex Hausdorff spaces. Here will be something more complicated, but I would like to accentize what these topoi and of course these objects are in abstract terms. I haven't talked about the question whether this map is continuous, because in the commutative case you get continuous functions between the spectra. I'm pretty confident that this can be seen as continuous in a suitable sense. In our example for the unitary group actions, we saw it mapped open subobjects to solve open subobjects, and well, that's a particularly simple situation. Well, so that should be more about this. And of course, the most interesting and the harder question is, can we go back? So if I understand times 1 and 2 a bit better, then I would like to see, is there a chance of defining back in this direction, going from the non-commutative spaces to the non-commutative algebras? And I'm really optimistic, and I believe that we can get into Charlie equivalence. Okay.
Questions? If you would have this non-commutative spectrum, what kind of physical entity would be encoded in it?
It's like a state space for a quantum system. So it is my idea that this thing, of course, should get more and more geometry step by step. And we have a strong analogy structurally between classical and quantum physics from this approach. So hopefully we will be able to develop geometric tools for this kind of non-commutative space in analogy to differential geometric tools in classical physics. So this is where this should go.
We use the presheaf category, but maybe B of A has a broken topology element that would help.
It is awfully hard to find interesting broken topologies. There's one thing you can also put, of course, the Alexander topology there. I haven't looked actually. I think it is in the domain, this concept. So should really check this before making any claims. Yes, this question of whether we would run like sheaves.
When you pass to this sort of different notion of the spectral presheaf, which where all of the abelian subalgebras have to contain the center,
Yeah.
does anything else break that has to be sort of patched up, or does everything else just sort of go through?
Amazingly, actually everything else goes through straight away, and also for other constructions we have in